Deterministic Finite Automata. The singular of automata is automaton. Deterministic finite automaton is defined by the 5-tuple Q, sigma, delta, Q0, and F, where Q is a finite set of states, sigma is a finite set of symbols, that is the alphabet, delta is a total function from Q times sigma to Q, this is the transition function, Q0 is an element of Q, that is the initial state, and F is a subset of Q, is a set of final state. We define the extended transition function, that is delta star from Q times sigma star to Q. Now look at this example. The left side is the transition graph and the right side is the formal definition of this automaton. This is a deterministic finite automaton and consisting of 4 vertices and 8 edges. Now look at the transition graph. So delta with Q0 and 0, it goes to Q3. Delta with Q0 and 1, it goes to Q1. Delta star with Q0 and 1, 1, it goes to Q2. Delta star with Q0 and 1, 1, 1, it goes to Q2. Delta star with Q0 and 1, 1, 1, 1, it also goes to Q2. And delta star Q0, 1, 1, 0, 1 also goes to Q2. Now Q2 is an element of F, so that is in this case only one final state, so that is the final state here. Now Q3 and Q1, they are both not final states. So a word W is accepted by an automaton M if W is encountered when we traverse from the initial state to a final state of M. In other words, all sequences of symbols that can be formed starting from the initial state to a final state. A language LM accepted by automaton M is the set of all accepted words by M. So that is LM equal to the set of W element of sigma star, where delta star with Q0 and W is an element of F. So go back in our example. What is the language LM of this automaton M? Now we are going to list some of the words accepted by this automaton, starting from the shortest one. So this is the list of some of accepted words. 1, 1 is an accepted word because we can go from Q0 with 1 to Q1 and with 1 to Q2, which is the final. 111 is an accepted word because we can go from Q0 with 1 to Q1 and with 1 to Q2 and take the loop to Q2. The same way is 1111 is also an accepted word, and also 11111 and so on. 101 is also an accepted word because we can start from Q0 with 1 to Q1 and take the loop once in Q1 and go to Q2 with 1. Now 1, 0, 0, 1, we can go from Q0 with 1 and then take the loop twice in Q1 and continue with 1 to Q2. Similar way for 1, 0, 0, 0, 1. Now we're going to take 3 times loop in Q1 and so on. Now if we take from Q0 with 1 to Q1 and then the loop once in Q1 and then continue with 1 to Q2 and go back with 0 to Q1 and go to Q2 with 1, then we're going to have 1, 0, 1, 0, 1. So the language LM is the set of all words on 0 and 1 that starts and ends with 1. So in the formal notation, LM is the set of 1W1 where W is element of sigma star. Now next example, design an automaton accepting the language in the bracket 0, 1 to the power n, where n is a natural number. So the set of natural number is the set of 0, 1, 2, 3, 4, and so on. Now we're going to list some of the accepted words starting from the shortest one. Now empty word is accepted this automaton. 0, 1 is also accepted. And 0, 1, 0, 1 is also accepted. 0, 1, 0, 1, 0, 1 is also accepted. And so on. So we're going to design an automaton accepting this language. I will start with Q0. And because the empty word is also accepted by the automaton, so Q0 is a final state. Then we create another state that is Q1 and put an edge from Q0 to Q1, label 0, and from Q1 to Q0, label 1. Now this is already representing the language, but this one is not deterministic, so we need to put or to create another state that is Q2 to make it deterministic. Now we see that from Q0, only H with label 0 going out, so we have to make another H label 1 from Q0 to Q2. And from Q1, we have to make another H label 0 to Q2. Then in Q2, we have to make a loop label 0 and 1. Now the state Q2, we call it trash state because it's actually nothing to do with the language, but to make the automaton deterministic, we need Q2. And Q2 is also called a trap state because once you arrive there, you will never go out anymore. So this is a deterministic finite automaton accepting the language 0, 1 to the power n, where n is a natural number.